Hello everyone, I'm Samson Prati, an interdisciplinary PhD research scholar in the Department of Electrical Engineering under the supervision of Dr. Swarup Sahu. Imagine the situation of a patient who is suffering from breast cancer and his cancer is detected at the early stage with conclusive evidence. He or she will be more happy than anyone else because the survival rate will go up because breast cancer is the most commonly diagnosed cancer in women and has the highest incidence of cancer in women. There are different techniques for the detection of breast cancer like X-ray mammography, ultrasound imaging, MRI, like magnetic resonance imaging, but all the previously techniques has some pros and cons. In this paper, radar-based microimaging is proposed as a method of detection. Having said that, I welcome everyone to my presentation on extracting the tumor or concealed object signature and its application in pinpointing the spatial location of the breast tumor or concealed object through existing MatLab-based microwave techniques using Vivaldi antenna. The outline of my presentation are introduction to breast tumor, where I will talk about explicitly different techniques of tumor detection along with their pros and cons. Then I will talk about the importance of microwave imaging, followed by phantom and antenna design for breast tumor. Then I will talk about the imaging algorithm and its results. Here, one thing let me clear, the imaging and its analysis is not restricted to tumor only, it's extended to concealed object too. At last, I will talk about the conclusion followed by future scope. Basically, tumor is a lump of tissue composed of abnormally growing cells. It is of three types called benign, potential malignant, and malignant. Benign tumor grows with uncontrollable speed but not affect the functionality. It is a stage for early detection of tumor. As mentioned previously, there are different stages techniques for the detection of tumor like X-ray mammography, ultrasound imaging, and MRI. X-ray mammography uses X-rays as the examination wave to pass through the breast, which is compressed by two plates. Ultrasound imaging system uses ultrasonic waves of 1 megahertz to 15 megahertz, while MRI uses magnets to generate a very strong magnetic field for the creation of a pathological image. While these methods have certain limitations, several published articles confirm that the severity and the harmful effects of the X-ray mammography. Ultrasound imaging may be difficult to detect and distinguish deep lying and solid cancerous tissue. MRI is good, but it is not cost effective. That's why we are looking for microwave imaging. Electromagnetic based microwave imaging for the detection of tumor is based on electrical properties of cancer as well as the surrounding tissues. The electrical properties of tissue include two main parameters called the relative permeability and the permeability. And the tumor detection is done on the basis of healthy and malignant tissue scattering signature. That is, we have to compare after getting the signature from both from the healthy tissue as well as from the tumor tissue, and the difference will tell whether the portion or if the portion is affected by the tumor or not. So coming to microwave imaging, the radar-based imaging has different states of data acquisition and analysis, starting from microwave signal generation by VNA and transmitted through transmitter and received by array of antennas, followed by CVD, OID, and 2D image obtaining. In the multistatic radar system, a synthesized pulse generated from a frequency sweep is beamed into the breast using a transmitter antenna and scattering signal received by one or more receiving antennas placed around the breast. Whereas in a monostatic radar system, a single antenna which acts as a transmitter and receiver, or two antennae where one acts as a transmitter, other as the receiver is utilized. The transmitting and the receiving antenna are connected to the VNA, and the time domain signals are taken from the VNA, which is further processed to get the final image of the tumor by CVD, OID, and the 2D image, where CVD stands for the complex visibility data and OID the object intensity distribution. So now we'll go for the MOT scanning and the data collection for the breast tumor detection. So first we'll go for the phantom and antenna design. So one can see it here, the design hemisphere of breast phantom. The hemisphere breast phantom has consisted of the three layers. One is called the skin layer, fat layer, and the tumor layer. The skin layer has a thickness of 2 millimeter, whereas a fat layer has a thickness of 68 millimeter. The spherical tumor, which has a radius of 5 millimeter, and both are embedded in the fat layer. The tumor is at a depth of 25 millimeter. Coming to the antenna design part, so a Vivaldi antenna of dimension 73.4 by 42 millimeter is utilized for the microwave imaging. The Vivaldi antenna has a bandwidth of 5 to 10 gigahertz, which covers the lower frequency as well as the higher frequency of the operation. The lower frequency of the operation allows for more depth penetration, which gives the shape of the tumor, and the higher frequency of the operation gives the higher resolution, and thereby it gives the finer details of the structure. The antenna has a gain of 10 dBi at 9 gigahertz. The antenna with high gain is ideal for basically the radar-based monostatic imaging, which can provide good scattering response from the target, and thus enabling us to get a good image of the MOT. The image of the antenna used for imaging with the phantom can be further analyzed in the next MOT design part. The scanning mechanism, the metal under test, is shown here. So one can see here the top view of the antenna of the best phantom, along in the second image, which shows the front of the antenna and the hemispherical best phantom. So one can see that the best phantom is scanned by 17 by 17 points. Hence, the antenna is moved row-wise by 17 points and column-wise by 17 points. Thus, a total of 289 points. The scattering parameters are measured and then which are utilized to obtain the 2D imaging plot of the MOT. As I've already told before, that our analysis is not limited to breast tumor detection. It is further extended to concealed object signature extraction too. So for that, we have two design, MOT design 1 and MOT design 2. So one can see the MOT design 1. In this case, the MOT is a FR4 sheet with a copper patch on top. An FR4 of dimension 200 millimeter by 200 millimeter is taken in this case. Copper of shape rectangle and triangle are made on the FR4 sheet, which is shown here. And coming to the MOT design 2, it's also the same, that is FR4 sheet with a complete copper patch on top of the FR4 substrate. And FR4 dimension 200 millimeter by 200 millimeter is also taken in this case. For the concealed object detection, we have to design an antenna. In this case, we have taken the same Vivaldi antenna with high dielectric lens for high directivity. So a Vivaldi antenna of 110.3 millimeter by 82.2 millimeter is utilized for microwave imaging. This Vivaldi antenna has a bandwidth of 1 to 14 gigahertz, which cover the lower frequency as well as the higher frequency of the operation. The lower frequency of the operation allows for more depth of penetration, which gives the shape of the tumor, and the higher frequency of operation gives the higher resolution. Thereby, it gives the finer details of the structure. The antenna has a peak gain of 12 dBi at a frequency of 11 gigahertz. The antenna with high gain is ideal for radar-based monostatic imaging, which can provide good scattering response from the target and thus enabling us to get a good 2D image of the MOT. The antenna scanning mechanism of the MOT design 1 and MOT design 2 are exactly the same whatever we have followed for the breast tumor detection. Here one can see the perspective view of the MOT design 1, and the second image shows the front view of the MOT with the antenna used for scanning the surface for design 1. Just like the design 1, we have for the design 2, we are following the same procedure but with a slight modification, which you can see the arrangement of this antenna as well as this MOT design 1. The figure 1 shows the perspective view of the MOT, and the figure 2 shows the front view of the MOT with the antenna used for scanning the surface of the design 2. One can see here three images starting from A to C. That shows the different stages in the detection of tumor from the hemispherical breast phantom. The first one is the 2D plot obtained after doing the IA50 of the obtained values, which is the color plot. But behind that, there are a lot of image processing algorithms and steps. So coming to the imaging algorithm, first what you have to do, we have to scan the MOT, the material under test, in such a way that one can see feet for 15 rows by 15 columns. Then we have to make sure that you know the number of points that you are scanning, how many positions you are taking row wise, and how many positions that you are taking column wise in order to form a matrix. After that, from the simulator, we have to obtain the scattering parameter like S11 versus frequency plot in a linear scale for the entire set of scanned points. Then we have to use the UFFT2 function to convert the frequency domain to the time domain. The resulting graph after the implementation of the above step, you will find that it's a decaying curve with various peaks. Then what you have to do, you have to take a maximum peak in each of the time domain plots for each step position of the antenna. Arrange each of the peak values at the top position to form a matrix. Then you have to apply various contours to get the various intensity levels. From the contour plot, we will get a color image that is shown here, so that the color bar intensity vary from low to high. Then we have to change the colored image to the equivalent grayscale image. After that, we have to do the breast tumor image. In order to get the breast tumor image, Then you have to do Gaussian filtering. So after performing the Gaussian filtering followed by image growing, we use to segment the tumor from the image. Here is the imaging results of the concealed object. This one is for the MOT design 1, and this one is for the MOT design 2. Coming back to the for MOT design 1, one can see the images from A to E. We show the different stages in the detection of the MOT. Figure 1 can see the figure V, which shows the 2D plot obtained after doing the IFFT of the obtained values, and the final one is the extracted shape of the object. In order to get the extracted shape of the object from the 2D plot, in the background there are a lot of image processing algorithms. The same also we can see here in case of the MOT design 2, where in case in the image B, one can see the 2D plot obtained after doing the IFFT to the obtained value, whereas the last one is the extracted shape of the object, and the third one is the grayscale image of the previous step. So in between there are a lot of image processing algorithms are going in, and that I'm going to explain. So first what we have to do, first we have to scan the MOT, that the material under test, in the required way, so that one can see 25 rows and 25 columns. In case of the breast tumor, we are taking only 15 to 15, but here we are taking 25 rows and 25 columns. So one thing one should clear, that make sure that you know the number of points that you are scanning, how many positions you are tracking row wise and as well as the column wise. And after that, you have to go to the EM simulator, the CSC studio, in order to get the S11 versus frequency plot in a linear scale for the entire set of the scan points. Then we'll perform the IF52 function to convert the frequency domain. We'll go to the time domain. Then one will see that the resulting graph after the implementation of the above step, one can see that it is a decaying curve with various peaks. So what you have to do, you have to take the maximum peak in each of the time domain plots for each stop position of the antenna. Then you have to arrange each peak values at the stop position to form a matrix. Then you have to apply various contours to get the final intensity level. From the contour plot, change to a suitable color map so that the color bar intensity vary from low to high. Change the colored image to its equivalent grayscale image, so that by using various image processing algorithms, we have to extract the object or metal from the original image. For the material under test, image global thresholding is used to segment the metallic part from the image. For the copper plate image, we have to use the Gaussian filter, followed by image growing, which is used to segment the copper part from the image. For the concealed object image, Gaussian filter is the best. Coming to the end of my presentation, that is conclusion and the future scopes, we show that a new and simple microwave imaging technique has been designed, and this technique is used to pinpoint the tumor as well as to detect the concealed object, and that has been introduced in this project through the simple image processing algorithms. Image segmentation, thresholding, superpixel, and filtering, these are the algorithms that have been heavily used to segment multiple targets from the 2D plot obtained from the time domain signals. This algorithm can be further extended to multiple tumors as well as for objects of different shapes. Here's the key reference that I have followed throughout the process of image algorithm development and as well as the Vivaldi antenna design. I would like to thank Dr. Moesh Panikkar, Associate Professor IIT Palakkad, for offering the image processing course and honoring the motivational live classes. I would also like to thank Dr. Loosuk, Research Scholar IIT Palakkad, for modifying the course and the constant help and support in antenna and design. Thank you.